Right. So very good evening, everyone. Uh, I'm Pratik, and we will be starting with aircraft propulsion today. This is the first lecture, and we will be starting everything from scratch. Hopefully, you people will understand the content. I will go through the syllabus, all the points in great detail. Any point you feel you have a doubt or you want me to explain things in more detailed manner, please stop me. I can unmute you as well, or if you want, you can drop a message in the chat. I will be able to answer your questions. All right, so I'll straight away start for aircraft propulsion. Now, before going and starting our topic of jet propulsion today, right, I want you people to first of all understand what you will be dealing in propulsion for the next month, for a next month, not month, also approximately 2 months, because we are doing two core subjects in parallel. So, when we talk about specifically propulsion, and when we talk about aircraft propulsion, there are two kind of engines which we look into. All right. One is air breathing engines. As the name suggests, you need air for these kind of engines. And I hope you people know that there are two families. One is gas turbine, and the other family is piston engine. Now, when it comes to gate syllabus, we don't have piston engine in our syllabus. Piston engines are also known as reciprocating engines. This is not part of our gate syllabus, so we will not discuss them in this course, in this lecture series. And your entire gate syllabus is basically gas turbine engines. So these are two basically the families of engines, air breathing. And if you see inside this, maybe you people have heard some keywords about it. If not, it's okay. Your whole syllabus will talk about this. We have various people sitting in gas turbine engine family like turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet, and there are many more, but these are basically coming in your gate exams, or to be very precise, used in the industry, used in the applications. Although scramjet is not, but still, it's a very common thing to be asked in your gate exam as well. So your whole aircraft syllabus, aircraft propulsion syllabus, will first focus on all of these engines. Each engine we will need to study separately. And this we are talking about as air breathing. Now, there are another set of engines which are known as non-air breathing, which doesn't need air. That means you can travel in vacuum. And the only name which came to your mind is basically rockets. And you know, rocket flies in vacuum, right? It goes way above the Earth's atmosphere. It can go to moon, Mars, many things it can do where we don't have air. So second kind of engine which we have in our gate syllabus are the rocket engines. So two specific engines. Once this whole series is done, ideally you should be able to solve each and every theory, numerical, and not only academic wise or gate wise. You should be able to answer all conceptual questions related to these engines, typically air breathing and non-air breathing, in which we will talk about these engines. And then rocket engine is your second unit, which we will start after finishing jet propulsion. Now, moving forward, how the propulsion engine looks like. A very typical example. This is not how each engine will look like. There is a small variations. But you will understand this in next 15 minutes, how beautifully the engine family is being constructed. Why you have 5, 6 engines inside it, and all these make sense. So when you talk about any engine, right, before going into this complicated diagram, I simply want to tell you one thing, and you people know this. If you want to move forward, definitely you need to produce some kind of force in the forward direction. Correct? And maybe you people have seen some movies like Gravity or Interstellar, or even not, you have seen your Diwali rockets and all these things, right? So whenever anything wants to move forward, in that unit, whatever, it can be a rocket, it can be an aircraft, anything. If you want to move forward in this direction, what you want is you want gases to come out at very high velocity. It's like you push something backwards so that you can move forward. This is the backbone of aircraft propulsion for gas turbine family. Although there are engines like turboprop which doesn't work on these concepts. We will discuss that shortly. But keep one thing in mind, whenever you want to move forward, you want your engine or your unit to expel the gases at very high velocity. It's something like you push it forward and then you move in the forward direction. Now the question comes, how we can increase this velocity. So keep this in mind, any engine, whether you talk about turbojet, whether you talk about turbofan, whether you talk about turboprop, typically ramjet, turboprop, turboshaft slightly varies. I don't want to confuse you. Any engine which, or even the rockets, the primary motive is how you will going to get this high velocity coming outside the engine, because in the end you want to move forward. Your whole engine design only work, and I'm making it very simple for you people, the only task of your engine is to produce this high velocity at the exit. And you will later see, higher the velocity, higher will be what we name it as thrust, and higher thrust means you will travel faster. And you know, engines can travel at subsonic speeds, supersonic speeds, even at hypersonic speeds. Again, if you don't know these words, if you're not familiar, it's perfectly fine. We'll move ahead. But keep one thing in mind, my whole lecture series on jet propulsion will be focusing only and only how we're going to achieve this high velocity. All right. Now, to make you understand this, I have taken a schematic diagram basically of turbojet engine, but this is just an example. We will talk about all engines. So what happens in these engines is your air enters inside the engine. Keep this in mind, you're going to put a cover to this engine and then it will be installed in your aircraft. If you remove this cover and look inside, you see some components and you need not to write anything, please. I will tell you, this is just an introduction. We will go into detail of each engines. Then we will write each component, their functions, whatever equations are required. We will write everything. Understand these 10-15 minutes first because I'm explaining you your gate syllabus. So when your air enters, and everyone knows air enters from atmosphere, correct? Atmosphere can be, if your aircraft is flying at sea level, you're about to take off, then air from sea level enters inside the engine. If your aircraft enters, or if your aircraft is flying at an altitude of 11 kilometers, then air enters at 11 kilometers, or 15, then at 15, and so on. Air enters. That means this air will have certain amount of properties. Again, I will go in detail about these properties today itself. I'm just writing it if you people agree. Let's say air enters at a velocity of, just as an example, 100 meter per second. So with this velocity, you exit. As a very basic thumb rule, if this engine is working properly, at the exit, let's take an example again. My velocity, let's say at the exit, should be equals to 500 meter per second. If your inlet velocity is 100, outlet velocity is 500, this 500 will going to provide you a huge push, and hence this engine will produce what we know as thrust in the forward direction. That's the whole motive. Now the whole concept of jet propulsion is how you will increase this velocity at the entry from 100 to velocity of 500 at the exit. If you understand this, believe me, your whole propulsion and your whole gas dynamics topics are over. Both of these subjects, although gas dynamics is part of aerodynamics, but both of these subjects only and only worry about this exit velocity. In the process, you will see There will be shock wave formation. In the process, you will see there are CD nozzles and so on. Again, if you have not heard these terms, please don't worry. It is my task and responsibility that you understand each and everything slowly and get conceptually strong. Now, please see what we will do. So, if you want to increase the velocity, a quick question from my end to all of you. Do you people agree that if your velocity is 100 and then at the exit you want 500, is it not that I want higher energy at the exit? Guys, yes or no? Do you people agree on this? At the entry your velocity is 100, at the exit you want velocity of 500. That means you need more energy at the exit. Correct? And everyone knows that energy is conserved. Energy can neither be created nor be destroyed. Again, this is thermodynamics law. I'm not going into that because it is not required, at least for today. But we know energy can't be created, can't be destroyed. Correct? That means somewhere, somehow, to increase this velocity from 100 to 500, you have to give some energy from outside to the system. So, this energy, in very layman terms, is nothing but fuel. Correct? So, air enters with some energy. You add some additional energy into the system. Your energy of the whole system becomes more, and with that higher energy, you come out with a higher velocity. If you don't burn fuel, your engine will never work. And this is not true for aircraft engines. It is true for your cars. It is true for your bikes. Even for your e-bikes, you are giving the electrical energy. In cars and bikes, you are giving again burning fuel. Unless and until you're going to provide energy from outside, you will not going to get rise in anything. As simple as that. You're going to get a good score if you give energy now. If you're not going to provide any energy now, output will not be good. As simple as that. Nothing works without energy input. All right. So thing is, we will going to burn fuel. So this part, if you see, is nothing but our combustion chamber in which air will enter. You will burn fuel, and fuel burned means more energy. And then with this high energy, you go out. This is fine. So everyone can understand why combustion chamber is present. But the question is why you need all these people who are making your engine so lengthy and big. Correct? So the thing is, it works something like this. Please neglect these images as of for time being. I'm just taking a help of a slide. Let me take slide here. So let's say this is your combustion chamber. This box is your combustion chamber. I'm just giving you an example. And in combustion chamber, you will put some flames by which you are going to burn the fuel. You need to ignite also, right? And keep this in mind, all fuels can only burn with air because they need oxygen to burn. So air should enter from here. Now what we will do is we will put some fuel over it. So we will have fuel nozzles which will spray fuel molecules like this. Your air comes like this. They both mix together, move forward, and you burn them. Once they are burned, you have high energy because energy of fuel is added. All right, this is how it should work. Now think in this way. I have a combustion chamber like this, everything same. And now my air which is coming is not coming like this. My air is coming, let's say I have this much amount of volume of air at the entry. This is my air. Air molecules are coming like this. Now, two things as a designer you people can do. One thing is, if you want to burn this air completely, you should make your combustion chamber very big so that every molecule of air enters. One thing. Second, what you can do is, and what you have to do is, if you put a fuel nozzle here, which is spraying fuel like this, if this is very big, right, you can imagine that this air will pass without burning with fuel. So you are wasting the air at the entry. Correct, right? To avoid this, what designer thought, let's do one thing. Before entering into combustion chamber and before adding fuel to it, what we will do is we will compress this air. So same air is compressed. This is a very simple word. You have done this throughout your life. If I'll give you a box or anything and ask you to shrink it, you can just compress it and keep it in a smaller place, right? That's what easily you people have done it. So what we have done, we have not reduced the amount of air. What we have done, we have simply excuse me, we have simply compressed the same volume of air into a smaller volume. But keep this in mind, molecules will remain same. The reason of this compression is now these people can easily enter into my combustion chamber and there will be less wastage. And you people will see in coming lectures, if the air molecules doesn't burn properly, right? At the exit, you will have, at the exit means here, at the exit, you will have poisonous gases coming out. You will see combustion chemical equations in the lectures. And if this combustion is not proper, if you people are not doing this compression properly and then this combustion properly, believe me, your aircraft will not be allowed to fly because at the exit, you can have poisonous gases coming out, which are not, you will not be allowed to fly with that particular engine. So combustion is very, very important, I can say, process. So to accomplish this compression so that you can have better compression, what people thought, let's put a compressor before a combustion chamber. And the whole task of this compressor is to compress the air. Even if you see from the entry, right? This is the entry, and at the exit, if you see, your compressor volume is reduced. Please don't worry, this is just an introduction. You will have each and every answer for each and every statement. Why this compression? Why these number of? Why this diagram looks like this? What are these individual things? Please don't worry about it. I will go in detail. But at least you people understood what this compression is doing before combustion chamber. Now, you will learn this, that this compressor will rotate at very high speeds. Now, it is really bad idea. I think I need to stop allowing people to annotate. I think some people are annotating on the slide. It's okay. Let's move forward. Just give me 1 second. Okay. So because this compressor is rotating at very high speeds, what people thought, it's very, very dangerous. Directly air enters and hit these blades. These are very expensive blades, guys. These compressor blades, you will find these are very expensive and very difficult to manufacture. So to make life easy for this person, there is an person before it which simply provides help for compressor. So it's simple words like this. Your compressor has to do proper work for combustion to happen. If your compressor is bad, your combustion is bad. If your combustion is bad, you're not flying. To make your compression better, you have installed an intake, which will take the air properly and give it to compressor. As simple as that, very layman terms. So people thought, let's have these three components: intake, compression, and combustion. Now, I just now explained that this compressor is rotating at very high speeds. Correct? If your compressor is rotating at high speed, someone has to rotate it, right? You will not going to sit on the engine on your aircraft and rotate it with hand. Someone has to rotate it on it. It has to rotate on its own, right? And the purpose of next component is that this component, which you name it as turbine, its motive is to drive this compressor. So what happens is this turbine will rotate and then this compressor will rotate. And keep this in mind. Why you want compressor to rotate? Because you want to compress the air. And I assume you people don't know that, sir, for compression, why you need to rotate. So you will learn this shortly why. So your compressor need to rotate, and to rotate that we have installed a person who will help compressor to rotate, which is nothing but your turbine. So after combustion, you have turbine. Why after only? That also we will learn. And once all these things are done, you have a proper exhaust pipe. Now this exhaust pipe can be of this shape, and you will learn later it can be of CD nozzle shape also if you want to work with supersonic flows. Again, don't worry about it. So if you broadly see this components, right, you have intake to help compressor. Compressor will help combustion. Then you have turbine, which will again help compressor. And then to get things out, you have used an exhaust pipe. This is basically layout of a gas turbine engine family. Later you will see, not later, in 5 minutes only, what different kind of engines and arrangements you can have. Now, before going further, give me a quick thumbs up. Is it making sense up till now, whatever I've said? Do you have anything in mind which you want me to repeat? If it's okay, please tell me. We'll move forward. Is it clear for everyone? Perfect. Let's go ahead. Keep this in mind. I have not yet started my topic. Yes, we will discuss this, Divakar. Let's do it very, very slowly. So just to give you an example and to give you a feel, this is how an actual aircraft engine looks like. This is a schematic diagram, which is basically for understanding things theoretically. If you see the next slide, right? This portion which you see from here till here is basically your compressor. And if you see in compressor, you see these kind of blades, right? And then you see another blade range, another, which in this slide is represented here. You see, they are representing one line here, another line here, another line here, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so many stages to be very precise. This is what's shown here. Then in this zone, you will put your combustion chamber because this is open to make you understand. And after this, you will have your turbine, which is again shown here. You can see how huge this engine is. And that's the reason this engine can produce thrust, which can propel your whole aircraft forward. And you have such big, huge aircrafts, right? So your engine also need to be powerful. So this is just for an illustration, how it looks like. Let's move forward. Again, coming back to academics. So same design I have given here in a slightly easier way. So let's understand what our GATE syllabus is. Why they want you to understand this GATE syllabus, why they want you to crack this GATE exam, and then why this is required to enter into a job after clearing your exam or after doing your higher studies. Your first topic is known as jet propulsion, which we will start today. This jet propulsion will talk about gas turbine engines, all engines. So turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet, whatever engine is present, we will talk about that engine in jet propulsion. All right, first topic. Second chapter, if you see in your GATE syllabus, you will find the word axial flow compressor. I hope you understood, because compressor is an important part of our engine. So we have to study about compressor, right? Why compressor has so many stages, why compressor is rotating, how compressor is compressing the air. You cannot say it is a compressor, so it will compress the air. It has to do something, right, to compress the air. So we will study everything about compressor. But the thing is, there are not only one compressor. There are two kind of compressors. One is axial flow compressor and one is centrifugal flow compressor. So we in GATE syllabus will understand both of these compressors. So this is chapter 2 and chapter 3. Then we will talk about axial flow turbine, this component. Definitely, we need to understand about turbine also, right? Now, you will see in turbine, there are other turbines also, radial turbines, steam turbines. In axial flow turbines only, you will read about impulse reaction. So there are so many turbines you will talk about in this particular unit. So this also makes sense. This should be part of our syllabus. Correct? Then, understanding all this, if you people agree, you people will, once your whole engines are ready, you will apply kind of similar concepts in rocket propulsion. But keep this in mind, these are two different people. This is air breathing engines. This flies very close to Earth. Whenever you move from one place to another, fighter aircrafts, commercial aircrafts, any aircraft which you see are nothing but these engines. And rocket, you people know, will go to very fast distance travel in vacuum. So it's altogether a separate topic which we need to study in detail. Correct? And then, last but not the least, we have to talk about thermodynamics, right? Now, this is my way of taking it. Some people might follow different route. When I start jet propulsion or any topic, I will make sure that all thermodynamic concepts are being covered in starting only. So we will talk about isentropic flows, we will talk about Brayton cycle, we will talk about internal energy, enthalpy, entropy, all these things when we are doing these particular topic itself. But still, eventually, you should know thermodynamics. And if you see your GATE syllabus, you will find thermodynamic basics of thermodynamic principles mentioned. Now, compressor is done, turbine is done. We have to study about combustion chamber, right? So if you want, you can name it as separate chapter, but I will study combustion chamber in chapter 1 only, because typically this is provided in all standard textbooks in this format. But if you want, you can name it as chapter 7, combustion chamber. It's altogether a separate component only, right? So we will study about combustion chamber. We have to. Then we will study about intake. Again, 100% we have to study about intake. You will see it is also known as diffuser. It is also known as inlet. Inlet, intake, diffuser, all are same keywords. So we will study this again in chapter 1. And then we will study about nozzles, which is our last component. So we will go in detail for compressor, turbine, combustion chamber, diffuser, nozzle. And then once you have studied everything, what we will do is we will talk about all sorts of engines. We will combine them, talk about turbojet. We will talk about turbofan. We will talk about turboprop. And typically we will talk about ramjet. All of your gate numericals from 2007 till 2025 will work on these three engines. There is only one question asked on turboprop, and believe me, that was just based on efficiency. So they are not never entered into this. And one theory question out of all these years, one theory question only asked on scramjet. So although we will cover this, we will understand the physics, we will solve some numericals, but the only one question asked on turboprop for 1 mark, one question asked on scramjet for 1 mark. All remaining questions are asked on these three engines. Absolutely. And once all this is done, we will talk about some topics like afterburner. If you have not heard about this, keep this in mind. This is like producing extra thrust by burning more fuel. Maybe you people have seen fighter aircrafts producing very high thrust by burning very large amount of fuel, and you can see huge amount of flame coming outside the engine, right? That is typically afterburners, and we will talk about optimization of turbojet, turbofan, and blah blah. Many things will come. Give me a quick nod, guys, and tell me if I'm making sense. You people are following me. First thing is your syllabus clear to you people? Absolutely. There is no confusion in this. Because when you're starting anything, you should be clear what you're going to do for the next coming days, right? Perfect. Now, this syllabus in your exam will, on an average, cover 20 marks. On an average. It can go to 18 and it can even go to 23, 24, 25. But if I take an average of all the years, 20, approximately 20 was in 2025 also. Yes, everything. As I told you, Vishesh, your steady flow energy equation or any thermodynamic zeroth law, first law, second law, third law, any law will be covered within these topic itself. And we have this separate topic also, right? If you go to your study material, I have provided this as a separate chapter itself. Gas dynamic is separate, Priyal. I'm only and only talking about propulsion syllabus. Gas dynamics is again asked for 6 or 8 marks separately. And if you're good in propulsion, you will be good in gas dynamics. If you're good in gas dynamics, you will be good in propulsion. So it works in both ways. All right. So it is asked for 20 marks. One thing. If I'll give you a breakage, this is approximately 6. I am again saying I have seen question papers. I'll show you this can go to 8 as well. Rocket again, typically for 6. So these two, chapter 1, which include combustion chamber, intake, nozzle, and all these engines, it's a huge topic, will cover 6 to 8 marks. Then your rocket will cover 6 to 8 marks, typically 4 to 6, 6 I can say. And then every year you have one numerical on compressor, one numerical on centrifugal, one numerical on turbine. And if you combine all this, right, it will approximately go to 20. Sometime it can go to 21. They can ask this one theory question for 1 mark, or maybe 1 mark theory question here. I hope you got an idea how your syllabus is distributed. Now, keeping this in mind, you should prepare your plan. You should not spend 1 month preparing for 2 marks for your gate exam. It is not ideal. But when you people are doing jet propulsion, you need to spend considerable amount of time, guys, because this is heavy. Many topics are included, and if you are good in jet propulsion, you are good in engines flying, you can understand all these things. Coming to next question, which I got very common, what are the books referred? So keep one thing in mind. I will be telling you books referred for each topic separately. There is not a single book which will cover everything. I told you in my previous lecture, I have uploaded that. Sayyid Ahmad, right? That's my favorite book for propulsion, which have everything. That's the only book. But there are other books which are really good in some topics. And when we are going in each individual topic, at that point itself, I will tell you which book to refer for which topic. And even for small subtopics, you need to refer some separate books. I have combined everything in your study material books. So once you have those books in your hand, you need not to go to separate books and you can save your time basically. I have already covered this part, which I have written here, rocket propulsion. And in rocket, you will learn all these things. Why you have first stage, second stage, third stage, why multi-stage rockets are designed. What do you mean by payload? What do you mean by strap-on motors? What do you mean by fuel and oxidizer carrying? And all these dual launch adapter, or every keyword you will understand in rockets, and eventually you will learn at what velocity you should fire your rocket if you want to go to moon, or how much fuel you need, how much oxidizer you need if you want to go to Mars, how much fuel you need, how much oxidizer you need if you want to go to moon, how much fuel and oxidizer you need if you just want to launch a satellite in an orbit, low Earth orbit, or in a geosynchronous orbit. All these calculations will be done in rocket propulsion. And believe me, guys, once you people are really good in rocket propulsion, after understanding this, they have beautifully framed your syllabus to transit to what is known as space mechanics. This is a separate subject for your gate, but keep this in mind. Once your rocket is ready, then only you can go to space, right? And then space mechanics will tell you how you will go. So if your Earth is here and this is your moon, do you want to go like this? Do you want to go like this? Or do you want to simply go like this? All these questions will be answered in space mechanics. But before that, you need to make your rocket ready, right? So this will be covered in propulsion syllabus. Once your whole syllabus is done, I want before starting jet propulsion, I'm starting jet propulsion now. You see what different kind of engines you have. You have a turbojet engine, you have a turbofan engine, you have a turboprop engine, you have a ramjet engine. These are the basic engines which you will see daily, and mostly of these engines you will be working after when you are starting the job, right? But one thing which is very common, if you see here you have combustion, here you have combustion, here you have combustion. Combustion and burner are one and the same thing, and here you have combustion. So you have to burn fuel no matter what engine. Then next thing which you see, each engine will have an exhaust. That means nozzle, 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 nozzle. That means whichever engine you talk about, gases has to come out, right? Then if you see this engine has a compressor, turbojet. This engine has a compressor. This engine has a compressor, but there is no compressor here. You see there is a word compression mentioned here, but keep this in mind, this is no compressor. You will learn this when we move ahead. Now comes turbine. You have turbine here. You have turbine here. You have turbine here. but there is no turbine here. So a ramjet engine, but if you see, you are using same components, but why you are naming different naming? Why you're saying this is turbojet, this is turbofan? It is because of how the engine starts. So if you see a first engine, you have an intake. You see, you just have an intake. If you see turbofan engine, what you're going to do is you will install a big fan inside the engine cover. And this is the engine. Believe me, guys, if you go to any airport, right? 99% of the times, the engine you will going to see is turbofan engine. When you're moving from Delhi to Bangalore, Mumbai, anywhere, local flights, you will be typically seeing turbofan engine. Even for international flights, you will see all turbofan engines. 99.9% aircrafts, you will see turbofan engine. So the only difference between turbojet and turbofan is that you have simply installed a fan before entering inside the engine. This is a fan. That's it. Now, if you remove this fan and put big propeller blades outside the engine cowling, keep this in mind. There is a basic difference. In turbofan engine, your fan is inside the engine cover. In turboprop engines, your engine cover is this, and then you have extended your fan outside and you have big propeller blades outside. You have seen these kind of engines also in your life. You have seen at the airports also, but very rare. So turbojet, put a fan, it becomes turbofan. Remove the fan, big put propeller blades, you have turboprop. And remove fan, propeller, compressor, turbine, what you have is a ramjet. You will not see this because typically this is used in missiles. And that's how, to make you people understanding and good in conceptual for all these engines, now you people can see how beautifully people have framed this gate syllabus, so that once you are done with this, you are ready for the interviews, you are ready for the job, you are ready for the gate exam, even you are ready for, if you want to write HAL exam, DRDO entrance, anything, you are ready if you have done all these things because you are ready with the concepts. Now, next slide is we will start our first chapter, which is jet propulsion. So today my lecture is starting unit 1, and we will cover all these things which I have mentioned here. But now I am zooming into this syllabus and we will discuss this. Tell me, guys, give me a quick nod if this is okay and fine for everyone. And give me 1 minute. I'll be back, guys. Please respond, guys. Okay. So if no doubt, let's move forward then. So this is our chapter 1, and we will be talking about all these engines. I hope you people understand the keywords now. I'm not going into each heading, but you will talk about thrust equation. We will see this now itself. Then you will talk about efficiencies. If you see here itself, we'll talk about diffuser. Here we'll talk about nozzles. So both topics covered here. Here only we will talk about combustion chamber and its chemical equations, which is from 2015 and 16 till 2025. Every year there is one question on this chemical balance. Even in 2025, 24, 23, 22, every year there is one numerical on this. I will show you the numericals. Once we study all this, we will enter into turbojet. We will optimize the turbojet engine, make it good. We'll go to turbofan, optimize it. We will go to ramjet and turboprop. Once all these engines are ready, we will talk about thrust augmentation. This is nothing but afterburner. There are another process also, but in your new GATE syllabus, they have updated the keyword as afterburner, but thrust augmentation is a catchy word. Now, books for this, I prefer this book. This is the best book. 100% you people should have it. I've already posted a video on this. You can download it from the website as well. This book is the only book which covers everything which comes in your GATE exam. So not only jet propulsion, it covers axial flow compressor, centrifugal flow compressor, axial flow turbine, complete jet propulsion, all these engines, efficiencies, whatever comes in your mind is present in this book. Apart from this, Cohen and Rogers is a good book, very, very good book. But the thing is, it will only cover turbojet and turbofan engines, but very thoroughly, beautifully. And as I told you, I have combined all of these things properly in your material books. So don't waste your time. If you need more content to read, let me know. I'll tell you which things you can do. But if you're doing it on your own or you want to read books, these are the two books which I feel. People try to follow veganation. I strictly say no, at least for jet propulsion. Veganation is good book for compressor and turbine, but absolutely no for jet propulsion. It is very basic. It will not help you to solve your gate numericals. Now, once I finish any lecture, I will come back to this slide and we will mark the topics which we have covered on that day. All right. So now I'm starting the topic of jet propulsion. So first thing is how thrust is being produced. All right. So as I told you, let's say as an example, this is any kind of engine, any engine. Let me zoom this. Now it can be anything. I'll take an example of turbojet for easiness. When this engine is flying, air will enter inside this and gases will come out. Why I am using the word air and gases? Because in combustion chamber, you have burned the air and air is no longer air now. It is being burned and gases are being produced. Yeah, fuel is added. All right. So when air enters inside the engine and exit, typically in most books, you will find this convention. Either you will find these conditions as A. A means you're standing or at the entry of engine and exit. Sometimes you will find this as I also, inlet. So sometimes you will find this suffix I also. Anything, please don't worry. Now when air enters with certain velocity. So you can say CA or CI. I'm writing both so that you people are comfortable. It can be anything. So this is the velocity of air with which air enters inside the engine. Now, air enters inside this engine with certain amount of mass flow rate. Now, what is mass flow rate? It is amount of air entering every second, kg per second, right? So if let's say, I'm just giving you an example, if let's say this is 10 kg per second, so 10 kg of air is entering in your engine every second. That's the meaning of mass flow rate. So in propulsion, we will never talk about mass. We will talk mass flow rate. How much every second mass is entering or leaving. So it enters at certain mass flow rate. And definitely your air will have some kind of pressure. So we will say PA. Atmospheric pressure you can keep in mind. People also use the word ambient pressure. All these are same thing, some catchy words just to confuse you, nothing else. And similarly, temperature of air. So basically, I have written some properties of air with which you are entering. Then you leave this, which are gases, and keep this in mind. In between, you have added fuel. Now, these gases come out, and typically in books, they will use the word CJ, and J comes for jet velocity. The jet which is coming out is the jet velocity. Don't worry if you write it as CE, it's okay. But I will follow CJ as the sign convention. So whenever you find or they ask in the gate numerical what is the exit velocity, I will write CJ is equals to question mark. Then these gases will definitely come out with certain kind of pressure. They will come out at certain kind of temperature. And this is question from my end to all of you. And you people tell me what you people agree. What will be the mass flow rate coming out? What will be the mass flow rate which is coming out? So do you people agree? No, constant, I agree. Mass flow rate of gases, I agree that also. But what is mass flow rate of gases? Can I say these are nothing but mass flow rate of air plus mass flow rate of fuel? Do you people agree on this? Because fuel is added, and this is basically how much fuel you are adding every second. So air enters, fuel enters, they both add up and come out as gases. Then the mass flow rate is Ma plus Mf, right? Guys, do you people agree on this? Give me a quick thumbs up if you are fine with this. Correct, right? Now, if this thing happens, your exit velocity is higher, your inlet velocity is lower, and this is how thrust is produced, which is captured using thrust equation. Now I'm giving you the equation. Please listen to me carefully. Thrust is basically represented as F. Thrust is nothing but a force. And we are representing this as F. Again, if you want, you can represent this as T. No one will say anything to you. I'm just following standard conventions. So thrust is basically denoted as F. And if you see some books, right, I will write this equation and then make you understand how this equation is making sense. So you will find this kind of equation. And I will explain each and every word here. Just be with me. This equation, which I have written here, is known as thrust equation. And this equation will give you how much thrust is being produced by that particular engine. Now, let's try to understand this. First of all, thrust produced by any, keep this in mind, we are talking about gas turbine engine family. The main reason of thrust production, and keep this in mind, guys, these are not basics. Everything of this is asked in your exam. I'll show you the question. Even if in 2025 you will find questions on this. So keep this in mind. We are not forming any basics. We are straight away starting the topic, which will solve gate numericals a lot. There in the on this equation itself, you will have more than 20 questions on your gate exam. I will show you the gate numericals. You will understand this. So thrust is basically consists of two parts. If you see first part, which I will go in detail, both actually. This first part is nothing but our known as momentum thrust. Second portion, which you see, this portion is basically known as pressure thrust. So total thrust is a combination of momentum thrust and pressure thrust. Now, what is momentum? Momentum is, if you see first part only, it is mass flow rate into velocity. Now, if you people have confusion here, absolutely fine. I am writing one equation for your note. You will understand the meaning of momentum. So let's write F momentum. So momentum coming outside the engine, that means at the exit, momentum at the exit is mass flow rate at the exit into velocity at the exit. So this is momentum at the exit minus momentum at the entry. Momentum at the entry is mass flow rate at the entry into velocity at the entry. And that's what is known as change in momentum. So your gas turbine engine works on concept of change in momentum. If you have change in momentum, you will produce thrust. Let me write this equation. So your exit momentum is m dot A plus m dot F. This is mass flow rate at the exit into velocity at the exit, which is Cj, minus momentum at the inlet is basically m dot A into Ci. So exit minus inlet is nothing but change in momentum. And this change in momentum is what is known as momentum thrust. Now the question is how this equation looks like this. Understand this now. What I will do is from this equation, I'll take m dot a outside. So if you take m dot a outside, here you have 1. This becomes m dot f divided by m dot a, and you have Cj here, and you have Ci here. And keep this in mind, this is also a bracket. I hope you understand. If there anything issue in maths, please tell me. So I've taken m dot a outside, and you end up with this equation. And just for easiness, and you will later understand why this easiness is required, we will write this term m dot f divided by m dot a as small f, which is known as fuel air ratio. And you will calculate this throughout your gate slips. Now, if you compare, if you write this as f, 1 plus f into Cj minus Ci, you will find this equation. And you know, if you write this equation, it is not easy to digest. But if you write exit momentum minus inlet momentum and then simply take m dot a common, you end up with your momentum thrust. So you have first component momentum thrust ready. The second component of thrust, which is pressure thrust, again, you people know pressure is force by area, right? This is our basic equation. So if you want to calculate any force, you need to multiply pressure and area. Correct? If you see, you have done the same thing here. Pressure multiplied by area. But which area? You see, your gases are coming out from this area, right? This is your exit of the engine. So we'll represent this as exit. And then, now this may be tricky to start with, but keep this in mind. PE is the pressure of gases which are coming out from the engine, and it is going into atmosphere, right? Atmosphere has same pressure PA here and PA here. Your aircraft is flying in same atmosphere. At the entry, at the front of the aircraft or at the back of the aircraft, your air properties will remain same, right? This pressure difference, PE minus PA, will going to create an additional thrust, which we name it as pressure thrust. If you combine these two, you have total thrust produced by the gas turbine engine family. Now, please listen to this very carefully. When I have given you thrust equation, I have not used any engine name. So this equation is valid for turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet, entire family. Please don't change this equation for an rocket will also work on this. Even rocket will also work on this. We will see how small changes here and there, but the basic equation, the backbone equation will remain as this. And this is how the thrust equation of a gas turbine engine family looks like, which is having two components, momentum thrust, pressure thrust. You see pressure multiplied by area. Momentum means mass flow rate into velocity, which I have seen here. You know what is each and every term here. This is mass flow rate. This is fuel air ratio. This is velocity at the exit, velocity at the entry, pressure at the exit, atmospheric pressure, area at the exit. I want each one of you to respond on this. Please tell me, guys, is this making sense? Are we clear absolutely up till now, whatever I have given you? Absolutely clear, right? Good that it is clear to you people. Okay. Guys, you people can see the screen, right? I hope everyone can see the screen. I think it should be visible now. Now you people can see, right? Okay, perfect. So we know something about at least how thrust is being produced. And the same thing I have discussed in thrust equation. Now, before going into static and stagnation properties, right? And before going into all these isentropic process, let me explain you a few things before before going into all these things. What is known as every engine will have an efficiency, right? So again, let me not write it as turbojet. Please don't worry about these headings, guys. Ignore this. Let me talk about efficiencies. Now, every engine should have an efficiency, right? And you want to design efficient engines. You want to have an efficient car also. You want to have an efficient two-wheeler also. Always you talk about efficiencies, right? Wait 1 second, I'm putting a charger here. Yeah. So what kind of efficiencies you people can define, or what kind of efficiencies are present inside the engine? Again, this is a general overview for all engines. You should apply this for turbojet, turbofan, ram. No matter what engine, we will apply these efficiencies, not for rocket. So efficiency works something like this. I'll explain you in the most simplest manner. Hopefully you understand this, and this will answer all of your gate questions also. So first thing is, what kind of energy input you are giving to the system? Can you people tell me what input you people give to the engine? An efficiency, you know, is always output by input, right? So in our engines, what kind of input we are giving so that we are producing thrust? We are burning. No, no, no. Input. Air is free, right, Paulman? Air is not what we pay for. Heat energy, right? Basically, we burn fuel which produces heat. So energy is the input, right? So first thing which your engine produces is known as heat power, heat energy. And this heat energy is basically given as how much fuel you people are burning. More the fuel, more the energy. Correct? Multiplied, you will find this term CV. Now, this is known as calorific value of fuel. This is also known as quality of fuel. This is also known as heating value of fuel. In simple words, understand one thing. If you use high quality fuel, energy will be more. If you use more quantity of fuel, energy is more. You people know. If you use petrol, your energy is different. If you use diesel, your energy is different. That is what quality of the fuel matters. Higher quality will give you more energy. So, quality of fuel multiplied by amount of fuel gives you what is known as heat power. This is the energy which we are giving to the aircraft. Correct? But the problem is we cannot utilize all the energy which we produce. Why? Always in reality, you have heat losses. So what happens? some amount of energy is lost to the atmosphere. And this is because of conduction, convection, radiation. You cannot get 100% efficiency, right? So there will be absolutely some heat losses, and that is bad. Now, whatever heat losses you have, after this, the remaining energy what we have with us is known as engine output power. Engine output power. Now, this is the energy which is left after heat losses. But the again problem is that we don't have this energy to utilize for our aircraft moving. We have further losses. To be very precise, these are mechanical losses. There is a catchy word to it. People say these are kinetic energy losses. I'll give you a simple example. In your engine, you have compressor rotating at high speed, turbine rotating at high speed. All these systems are resting on bearings. Your shafts are rotating. Every component has some losses, right? You cannot design a 100% mechanical system. And hence, these losses will also eat your energy. And the remaining what you have is known as thrust power. Remaining energy what you have is known as thrust power. This is the energy which is available to us to fly. With this energy, you can make your aircraft fly, guys. You, even though, keep this in mind, you are burning this much fuel, you are getting this much energy, but the useful energy which you have after all losses is known as thrust power. Now we need to write expressions for this. Correct? So first efficiency designed or defined for aircraft is the ratio between thrust power to engine output power. Efficiency is output by input, right? So output is thrust power, input is engine output power, losses are kinetic energy losses. If you take the ratio between these two, I will write all these efficiency in detail. Let me first draw this in table. This is known as propulsive efficiency, eta P. So the first efficiency I'm talking about, all right, is known as propulsive efficiency. This is sometimes also known as, because of the name of the scientist, it is also known as fraud efficiency. It's a name of a scientist, guys. And this is basically denoted as eta P. So what is eta P? Eta P, if you come from the ratio, and this expression is itself asked in your exam. Eta P, one basic expression is, it is the ratio of thrust power to engine output power. That's how the efficiency is defined. Now, don't forget, I will go in detailed derivation for this. All right, just give me some time. Just be with me and try to follow as much as possible. If you feel anytime you have a question or a doubt, please stop me. I will try to go in detail. I will try to explain. I will answer your question, Vedika. Just give me a few minutes. I will write each and everything. Now, if you take the ratio between engine output power to heat power, this efficiency is known as thermal efficiency. It is taking care of thermal losses, right? So the ratio of engine output power to heat power is known as thermal efficiency. So the next efficiency we're going to define will be known as thermal efficiency of the engine. And it is denoted as eta pH, thermal efficiency. And if you define it in the formula now, this is engine output power divided by heat power. This is the second type of efficiency defined for any gas turbine engine family. And they will ask in your exams, they will ask thermal efficiency directly, they will ask propulsive efficiency directly. At least we know some basics now. Then, if you take the ratio between thrust power to heat power completely, this is known as overall efficiency. And this efficiency, I'll write it here as overall efficiency of the engine, eta O. And if you just learn from the formula, I think it is easy for you people to learn now. This is nothing but thrust power divided by heat power. Correct? Now, coming back to more detailed about this plot. So first, you people understood what is heat power. Heat power is m dot f into CV. Just for your easiness and Vedika to answer your question, CV here is calorific value of fuel. This is also known as heating value of fuel. You will find all these words in your questions. They will use these words in your gate questions. You can also name it as quality of fuel. I hope Vedika, you got your answer. So this represents what kind of quality of fuel you are using in your engine. Is this clear, Vedika? All right. Now, moving forward. What is this thrust power? We need to write expressions, right? We know thrust is denoted as F. Thrust power, which is, let's say, thrust power, is known as thrust multiplied by the velocity of the aircraft. If you see CI is the velocity of air entering inside engine, and velocity of air entering inside engine is nothing but velocity of aircraft, right? See, when you have an aircraft, your air is still and your aircraft is moving forward with a velocity of CI. So inside your engine, air enters with a velocity of CI. That's the reason it's one and the same thing. So in your exams, they will say aircraft is flying with a velocity of this much. That means they have given you CI. So velocity of air or velocity of aircraft is one and the same thing. If you take thrust and multiply CI to it, you will get what is known as thrust power. All right. Now, what is propulsive power or what is engine output power? Now, engine output power, again, we will do these kind of small derivations here and there if it is required. For time being, let me fill this table so that you can just remember this image in your mind and you can answer all efficiency related questions in your gate exam. And this is easiest way to learn efficiencies also, right? Engine output power is basically half m dot A, which is mass flow rate of air, into Cj square minus Ci square. This is known as engine output power. Write it. We can write this expression later also, and we can derive this expression also. Now, Engine output power, if you people agree, gives you some kinetic losses, and in the end, you have thrust power. Although not required, I can easily skip this part. No one will ask questions on this in your gate exam also, but I can write this expression for your complete theory. This kinetic energy losses is basically known as half of m dot a into Cj minus Ci whole square. Just see the difference between the two people, guys. Propulsive power or engine output power basically is Cj square minus Ci square, whereas kinetic energy losses is Cj minus Ci whole square. I hope you understood the difference. Sometimes people find that these two are exactly the same thing, but they are not. All right. So engine output power minus these losses, you should get what is known as thrust power. Now, what I'm going to do is I'm going to write some expressions for efficiencies. Please be with me. I need to give you a brilliant note also, which will try to conclude these topics which we have done today. What do you mean by this? Let's see. So what is first efficiency? First efficiency is propulsive efficiency, that is thrust power divided by engine power, which we have written here. Thrust power divided by engine output power. What is thrust power, guys? Thrust power is thrust multiplied by Ci. I'm simply writing that expression now, divided by engine output power. Now, if you want, you can write engine output power as this expression. Or if you people agree, can I write engine output power as thrust power plus losses? Guys, I need yes or no from you people. Can I write engine output power is nothing but losses plus thrust power? Guys, yes or no? And you absolutely don't need to remember this derivation. Final expression is asked, I told you, maybe 5, 10 times in your gate exam. So engine output power I am writing as thrust power plus my losses. Losses are half of m dot a into Cj minus Ci whole square. I end up with this expression. Now again, anything which I block, you have to learn for your gate exam. So this equation, basic formula, you should know. Then whatever derivation I'm doing is for your understanding. You can skip this derivation. Final expression which we will get, we will learn that expression. All right. Now, guys, please listen to this. This is an important note. I should have done it before, but let's do this note now here itself. Most of the times in your gate exam, very, very important note, or you can mark this as 100% for your gate exam. 100%. The note is, if in your gate exam they will say PE equals to PA. Now, what is PE and what is PA? PA is the pressure of gases in the sky, in the atmosphere, where your aircraft is flying. And PE is the pressure of gases which are coming out from your engine. I'm not naming this. Although this is known as optimum expansion, but I don't want to confuse you now with these words. Let's say if in the exams they say your gases are coming out at the same pressure which is present outside. In this case, can you people tell me what happens to this pressure thrust? I just want you people to tell me this. If PE equals to PA, your pressure thrust will go to zero, right? So if this note is given in your gate exam, let me write it, but don't worry, I will explain this in detail. This is known as optimum expansion. Please don't worry about this. We will talk about over expansion, under expansion, optimum expansion, all things in detail. But as of now, let's say PE equals to PA, then your thrust expression is basically only momentum thrust. So pressure thrust goes to 0. Easy, digestible. But they will do one more thing in your gate exam. What they will say is that the fuel air ratio is very, very, very small quantity. And you know, amount of air entering will be 100 kg per second, 200 kg per second, but fuel burning will be 1 kg, 2 kg. That's the only amount of fuel you burn, right? So this ratio becomes very small. So they say, in simple words, they will say neglect fuel air ratio. They will use this word in your gate questions. And you will understand this. If this value is, let's say, 0.001, 1 plus 0.001 is nearly 1, right? So we will going to neglect this F. And if you neglect this F, what is your thrust equation, guys? M dot A into Cj minus Ci. Do you people agree on this, guys? Everyone agrees on this? This is the most easiest and simplified equation asked many, many, many times in your GATE exam. But keep this in mind. This is most accurate equation without any assumption. Then you have one, not the assumption, without any point. If you have optimum expansion, then only you make this term as 0. And then if you neglect these small, small things, you end up with a very simplified expression. People have done it so that they can ease the calculations, no other motive. Now, if you keep this note in mind, I'm going back to my efficiency expression. Can I write this expression as, A minus B whole square? Can I take M dot A into Cj minus Ci as thrust? Let me write that expression. After all the assumptions, this was our thrust expression, right? So I'm taking this M dot A and one bracket out of it. Let me write it. So if anyone having any confusion, just follow. If it is not, I will write it. I am writing this as F divided by 2 into Cj minus Ci. Everyone agrees on this step, or anyone having any question or concern on this? Clear, right? And then in this step only, so that I need not to write this again, I'm taking Ci outside. I'm taking this Ci common, guys. So when you take this Ci common, do you people agree if I'll write this as, sorry, now this is the expression I want you to be comfortable mathematically. Now we have done this. So if you people agree, I can cancel out this, and this term. I can take F into Ci common from denominators and it get cancelled out with the numerators. Correct? And what we are left out with? 1 divided by 1 plus 1 by 2. And now this Cj divided by Ci plays a very significant role in gas turbine engines. We will name it as alpha. Let me explain this. Before that, mathematically, I want to finish this expression. If you simply take the LCM here, send it to numerators. You can even try. You need not to take my words. Take a try. You will get this expression as 2 alpha divided by 1 plus alpha. So after all of these derivations, which I have not blocked, you will not learn a single word what I have written in between this formula. And after all these mathematical manipulations, we end up with this formula where if you see alpha is basically Ci divided by Cj. This is also known as speed ratio, where Ci is your velocity at the entry of the engine and Cj is the velocity at the exit of the engine. And if you know velocities, you know alpha. If you know alpha, Simply substitute the value of alpha here. And what we will get? We will get the efficiency of the aircraft. Believe me, guys, this is asked a lot in your gate exam. And I have blocked this, meaning you have to remember these formulas for efficiency. So we have learned first efficiency, which is propulsive efficiency, which is nothing but the ratio of thrust power to engine power. Give me a quick nod if this is fine and okay for all of you. Is this making sense? Are we clear? Clear, right? Second, you need not to do much manipulations. Second efficiency is thermal efficiency, which is engine output power divided by heat power. If you want, you can write the expressions. I just want to write it so that you people are okay with your notes. Engine output power is nothing but half of m dot a into cj square minus ci square divided by what is heat power? M dot f into cv. So you can learn all of these formulas. Now, if you open books, right, people write this m dot f by m dot a as f also. So if you people understood, then it will be clear to you. You will find this formula also in many of the books. Are we okay in this formula? It is nothing fancy, right? Guys, are we okay? You know, fuel air ratio is nothing but amount of fuel divided by amount of air, right? So, same equation, right, written in a different manner. And similarly, if you want, you can write thrust power as thrust divided, thrust into velocity is thrust power, heat power is m dot f into cv. Nothing else, nothing fancy. These are more than enough formulas. And I'm not saying previous year gate questions. No one can ask any question on efficiencies apart from this plot. No one can ask any question apart from this thrust equation. Any numerical, any theory question, whatever multiple choice, multiple select should be answered from these concepts only. The only thing is we need to practice questions. They will try to jumble up keywords. They will try to confuse you with give some given statements. We just want to practice, and that's what we are doing this for the entire year, right? We're just practicing more questions, practicing more numericals so that you have doubt and you can get it sorted and clear. Now, I can do multiple things in this, which we will do tomorrow. Not, I will not want to push everything in one lecture because this is first lecture. I want to keep it uh, proper, not too long. What we will do is we will derive this thrust power expression in next lecture. We will maximize it and then we will see different conditions. Now, before wrapping up and opening for doubts, this is the point I was making. If you go into the syllabus now, today in lecture, we have discussed about thrust equation and we have discussed about efficiencies. And that's how I will be talking about each and every topic and each and every topic numericals. Now, if you see my whole slide, once we are done with all these things, right, we will solve a very big numerical on turbojet engine. This will open many concepts in your mind. Believe me, you will become super strong in this topic once you do this numerical. Once we are done with this, then we will go to second engine, like turbofan engine, and we will solve a big numerical on turbofan engine. I'm telling you my process, how we will do this lecture. And same thing you will do on ramjet, scramjet, turboprop, and so on. Now, just to show you, because you people should know how lectures are being conducted afterwards, I want to show you my another slide here. All right, just give me 1 minute and it will be ready. Let's say I have opened this slide. Once these topics are done, we will enter into gate numericals. Now, the reason I'm showcasing this is I'm start doing numerical on 24. if you see the years now in 24 itself, you have 1, 2, 3, 4. You can imagine what jet propulsion is doing. Then we will go to 23. See how many questions in 2023. And this is absolutely jet propulsion, guys. This is not complete propulsion. This slide has no question from axial flow compressor, axial flow turbine, rocket propulsion, thermodynamic basics. No, this is only and only jet propulsion. If you see 1, 2, 3, 4, 5, 6. 6 questions in 2023. And if you count the marks, right, this is a 2-mark question. 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 So 8, 1, and 1. So total 10 marks, only one chapter. I'm not saying whole syllabus itself, only one chapter of jet propulsion. Then we will go to 2022, 21, 2019. And because I have limitation of slides in one option, I'll show you this also. Just give me 1 minute. We will do this from 2007 till 2025. So if you see, I've started 2007, and if you go, I will go till the very end. You can see how many questions we need to practice. This is going till 2019, 2018, and 2019 with the next slide. You can see 50 questions already covered, somewhere around 50 questions. So in jet propulsion, they have already asked 80, 90, 100 questions in your gate exam, guys. I hope you imagine why I am so much stressing on this topic. And if you are making this topic stronger topic of yours, right? You are in a position in first lecture only to score around 8 marks in your gate exam. I told you very conservative 6 marks, but you can see it can even go to 10 marks in your gate exam. And this is the reason it's a huge topic. I'm open for doubts now. If you have anything, please tell me, guys. Otherwise, we'll wrap it up for today. Tell me, guys, please.